Welcome to this exploration of the technology that defined local area networking. In 1976, Robert Metcalfe and David Boggs published Ethernet Distributed Packet Switching for Local Computer Networks in the Communications of the ACM. This paper described a networking technology that would become ubiquitous, the standard way computers connect within buildings, offices, and homes. Today, Ethernet is everywhere. Let's understand how it began. By the mid-1970s, computers were becoming smaller and more numerous. Mini computers and personal computers were emerging. But how should they communicate? Wide area networks like ARPANET connected distant sites over telephone lines, but they were expensive, complex, and overkill for computers in the same building. What was needed was a local area network, a LAN, optimized for high speed, short distances, low cost per connection, easy installation, and reliability. Metcalfe's key insight came from an unlikely source, the ALOHA network in Hawaii. ALOHA was a radio network connecting Hawaiian islands. It used a simple protocol. When you have data to send, just transmit. If two stations transmit simultaneously, they'll collide and both will fail. Wait a random time and try again. This was contention-based access. Stations competed for the channel rather than taking turns or being assigned slots. Metcalfe saw that this approach, adapted for wired networks, could be the basis for simple, effective LANs. The work happened at Xerox Palo Alto Research Center, one of the most innovative research labs in computing history. PARC was developing the Alto computer, a pioneering personal workstation with a graphical interface. They needed to connect Altos to each other and to shared resources like printers. Robert Metcalfe was hired to solve this problem. With David Boggs, he developed Ethernet, named for the luminiferous ether that 19th century physicists believed filled space. The first Ethernet ran at 2.94 megabits per second, connecting 100 Altos and laser printers. The paper describes Ethernet's key components: the ether, transceivers, and controllers. The ether is a passive coaxial cable serving as a broadcast medium. All stations connect to the same cable. Transceivers are hardware that connects stations to the ether, handling transmission and collision detection. Controllers are interface hardware in each station, managing packet framing and the access protocol. The system is broadcast. When one station transmits, all stations receive. But only the address station processes the packet. Ethernet uses CSMA CD, carrier sense multiple access with collision detection. Carrier sense. Before transmitting, a station listens to the cable. If another station is transmitting, wait. Multiple access. All stations share the same cable and can transmit when it's free. Collision detection. While transmitting, a station monitors the cable. If it detects a collision, it stops immediately. When a collision is detected, a jam signal is transmitted, then stations wait a random time and try again. The beauty of CSMA CD is its simplicity. No coordination needed. Efficiency under light load, fairness, and self-healing. Ethernet packets, called frames, have a simple structure: preamble, destination address, source address, type field, data, and CRC. Every Ethernet interface has a unique 48-bit address, often called a MAC address, assigned by manufacturers. This means no two devices worldwide have the same address, devices can be moved without reconfiguration, and packets can be addressed to specific devices or broadcast to all. The 48-bit address space seemed enormous in 1976. Today, with billions of network devices, we're glad they planned big. The paper describes the first Ethernet at Xerox PARC, 2.94 megabits per second data rate, coaxial cable spanning 1 kilometer and 100 connected devices. The system connected Alto workstations, file servers, and the world's first laser printers. This was the environment where modern desktop computing was invented. Key design choices that made Ethernet practical included a broadcast medium, statistical multiplexing, best effort delivery, minimum packet size, and maximum cable length. Ethernet evolved dramatically from 10 base 5 to 10 base 2, then 10 base T. It continued to evolve with 100 base TX, 1000 base T, and beyond to 10 G base T, and even 400 gigabits per second. The physical medium changed completely, but the frame format and addressing remain recognizable descendants of the 1976 design. Modern Ethernet networks use switches, not shared cable. Original Ethernet used one shared cable, leading to collisions. Hubs replicated signals, still a shared medium. Switches learn which stations are on which ports and forward packets only where needed, making each link dedicated. With switches, CSMA CD became irrelevant, as there are no collisions on dedicated links. But the frame format, addressing, and protocols remained. In 1980, Digital Equipment Corporation, Intel, and Xerox published the Ethernet specification, opening it to competition and standardization. IEE standardized Ethernet as 802.3 in 1983 with some modifications. The DIC's Ethernet 2 frame format remains common for IP networks. Robert Metcalfe later formulated Metcalfe's law. The value of a network is proportional to the square of the number of connected users. This helps explain network effects, why Ethernet dominated despite alternatives, why the internet grew explosively, why social networks are winner-take-all. Many LAN technologies competed with Ethernet, such as Token Ring, Token Bus, FDDI, and ATM. Ethernet won because it was simpler to understand and implement, cheaper, good enough performance, and adaptable. Today, Ethernet is ubiquitous in data centers, offices, homes, industrial settings, automotive, and carrier networks. Wi-Fi is essentially wireless Ethernet, sharing the same frame format and addressing scheme. Your laptop's Wi-Fi connection speaks the same protocol family as wired Ethernet. Packets flow seamlessly between wireless and wired networks. Modern Ethernet cables carry power through Power over Ethernet, delivering up to 90+ watts. PoE powers Wi-Fi access points, IP cameras, VoIP phones, and IoT devices, simplifying installation with one cable for data and power. Ethernet, distributed packet switching for local computer networks, made lasting contributions. The CSMA CD protocol, the frame format, performance analysis, the LAN concept, and open design. Robert Metcalfe left Xerox in 1979 to found 3Com, commercializing Ethernet. He became an entrepreneur, venture capitalist, and pundit. In 2022, Metcalfe received the Turing Award for the invention, standardization, and commercialization of Ethernet. Ethernet's success offers lessons. Simple beats complex, good enough is good enough, standards enable ecosystems, adaptability matters, and getting the abstraction right. The 1976 paper introduced a technology that would connect the world's computers. Metcalfe and Boggs designed a simple, practical system for local networking. They analyzed it rigorously, built a working implementation, and published their work openly. That openness was crucial. Ethernet became a standard that multiple vendors could implement, creating competition that drove down costs and improved quality. Today, whether you're in a data center with 400 Gbps connections or at home with gigabit Ethernet behind your router, you're using technology that descends directly from that Xerox PARC experiment. Ethernet didn't just connect computers. It showed that local area networking could be simple, affordable, and universal. And it still is.